With each fascinating picture captured by the James Webb Space Telescope, it continues to gather insights from various corners of the universe, including planets within our own solar system. A year ago, we witnessed our first significant glimpse of images showcasing the Carina Nebula, Stephan's Quintet, and, most strikingly, the mesmerizing Deep Field image. This extraordinary picture vividly depicts numerous galaxies resting in the vast expanse of the universe, fulfilling expectations. As anticipated, the James Webb Space Telescope has proven to be a marvel. It has, in fact, unveiled objects that challenge deeply entrenched cosmological theories. These astonishing revelations are now being referred to as universe breakers by cosmologists, mysterious phenomena with the power to upend existing ideas. The reasons behind these discoveries remain cloaked in mystery, throwing our speculations and hypotheses into disarray. So, what's the latest scoop from the James Webb Telescope? What groundbreaking new discoveries has it revealed that were previously unknown? Join us as we delve into its findings, including evidence suggesting the presence of another universe, one that challenges the standard understanding of the Big Bang. Our universe, as we've long understood it, emerged from a hotter, denser state through a theory known as the Hot Big Bang. This concept, a monumental scientific achievement over the last century, gained overwhelming support in the 1960s with the discovery of the cosmic microwave background, CMB, a remnant from the early hot and dense state. Over time, the Big Bang has remained the prevailing theory explaining the origins of our universe. However, new and significant observations have led cosmologists and astrophysicists to reconsider both the ongoing expansion and the Big Bang itself. Despite these challenges, alternative theories have struggled to gain traction, and the theory of the universe's origin continues to dominate. According to this prevailing view, the universe's beginnings involved a smaller, denser state in the distant past. The presence of radiation, like photons, indicates that the universe was hotter at its inception and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels approached a point where traditional laws of physics would collapse, around 10^3 seconds after the beginning. In this incredibly brief span, small distances, short timescales, and high energy levels challenge our understanding. Rewinding the cosmic clock to the hypothetical zero point, if the universe began as hot and dense, it would have expanded and cooled, producing vast quantities of particles and antiparticles. As temperatures dropped, excess particles were annihilated by radiation. The breakdown of electroweak and Higgs symmetries led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles like quarks and gluons. The fusion of protons and neutrons led to the creation of light nuclei such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions underwent expansion due to radiation pressure, followed by gravitational collapse, leading to the formation of large-scale structures. Approximately 380,000 years after the Big Bang, the universe cooled enough for stable neutral atoms to form. This marked a critical stage where photons decoupled, and their wavelengths stretched as the universe expanded. The discovery of the cosmic microwave background confirmed the Big Bang as the most supported explanation for the universe's creation. Big Bang versus steady-state theory. While most cosmologists and astrophysicists embraced the Big Bang theory, steadfast proponents of the steady-state theory, like Fred Hoyle, continued to defend increasingly doubtful ideas despite overwhelming evidence. The evidence presented was conclusive. The cosmic glow displayed remarkable consistency, resembling a perfect blackbody spectrum, with no connection to known objects in the universe. Despite this, Hoyle and his supporters persisted in undermining scientific progress by advocating scientifically untenable ideas. Meanwhile, the fields of space science and cosmology underwent tremendous advancements from the 1960s through the 2000s. Cosmology, in particular, made significant strides in mapping the universe, describing its large-scale structure, and studying the formation, evolution, and dynamics of galaxies and their stellar populations. Yet, even with these advances, anomalies persisted, challenging explanations within the framework of the Big Bang theory. One notable anomaly is the absence of predicted relics, such as magnetic monopoles or particles from grand unification. These issues have led many to rethink aspects of the theory. The universe we observe today seems to require forces beyond our current understanding. These forces remain elusive. At its inception, the universe required a precise rate of expansion to balance overall energy density, something the standard model of cosmology struggles to explain. This led to neither perfect equilibrium nor sufficient time for energy exchange across different regions of space. Given the universe's vastness and its ongoing expansion, these inconsistencies present significant challenges to cosmology and mainstream scientists. The inflationary model and its challenges. While existing theories fail to account for observed anomalies, two approaches are being pursued: refining current theories or considering alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang model. The inflationary model addresses many of the Big Bang's inconsistencies by proposing a brief but immense exponential expansion of the universe in its earliest moments, fractions of a second after its inception. This rapid expansion would explain the observed uniformity of the cosmic microwave background, CMB, the absence of magnetic monopoles, and the universe's large-scale structure. Essentially, inflation posits that a tiny region of space, governed by quantum fluctuations, expanded to create the vast cosmos we see today. Quantum fluctuations and structure formation. During inflation, quantum fluctuations, minute variations at subatomic scales, were stretched to cosmic proportions. These fluctuations became the seeds for the formation of galaxies, clusters, and other large-scale structures we observe today. Areas of slightly higher density attracted matter through gravitational collapse, eventually forming stars, galaxies, and other cosmic entities. However, while inflation has been successful in addressing several key issues, it is not without challenges. Critics of inflation point to a lack of direct evidence for the inflaton field, the hypothesized energy field driving inflation. Furthermore, the exact mechanism that triggered inflation, as well as how and when it ended, remains speculative. These unresolved questions leave room for alternative models and theories. The multiverse hypothesis. One of the more controversial implications of inflation is the potential existence of a multiverse. If inflation occurred, it might not have been a singular event. Instead, it could have occurred in countless other regions, each spawning its own bubble universe with unique physical laws and constants. This idea, though speculative, opens fascinating possibilities for the nature of reality. However, it also presents a challenge. If other universes exist, they are likely beyond our observational reach, making the hypothesis difficult to test or falsify. James Webb Telescope's role in challenging assumptions. Enter the James Webb Space Telescope, JWST, whose unprecedented sensitivity and resolution have provided insights into the universe's earliest epochs. By observing galaxies formed just hundreds of millions of years after the Big Bang, the JWST has revealed surprising details that challenge established theories. For instance, unexpected galaxy formation. The telescope has detected massive, mature galaxies existing far earlier than models predicted. These findings suggest that galaxy formation occurred more rapidly and efficiently than previously understood. Potential anomalies in star formation. Observations hint at stars forming at rates and under conditions not fully explained by current cosmological models. Some of these stars appear to lack heavy elements, raising questions about the processes of stellar evolution. Dark matter and energy insights. Data from the JWST is providing new constraints on the distribution and behavior of dark matter and dark energy, potentially reshaping our understanding of these enigmatic forces. A universe beyond the Big Bang. The JWST's findings have reignited discussions about whether the Big Bang alone can fully explain the universe's origins. Some cosmologists propose alternative models, such as cyclic or bouncing universes, where the cosmos undergoes infinite cycles of contraction and expansion. Others explore quantum gravity theories that seek to unify general relativity with quantum mechanics, offering insights into the universe's earliest moments. These alternative theories, while speculative, reflect the healthy skepticism and creativity driving modern cosmology. They also underscore the importance of tools like the JWST, which continue to push the boundaries of what we know, and challenge what we think we understand. Viewpoint expansion proposes a concise period of rapid expansion that smooths the universe, giving it uniform properties. It addresses the horizon problem and predicts the evolution of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns and changes, supporting its validity. Despite alternative theories, inflation's scientific strength remains unparalleled. However, despite past contributions to general relativity and singularities, Roger Penrose's work, alongside his collaboration with Stephen Hawking, failed to match the progress of inflation in explaining the earliest moments of the universe. Recently, there has been focused work attempting to undermine the legitimacy of the inflation theory, promoting conformal cyclic cosmology, CCC. However, CCC is inherently flawed from a scientific standpoint. The key distinction lies in their predictions. Conformal cyclic cosmology suggests that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. On the other hand, the inflationary theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang era. James Webb Telescope's revelations. Astronomers quickly recognized anomalies in the images sent by the James Webb Space Telescope, JWST, starting in 2022. These revelations could necessitate a reassessment of key aspects of the universe's origins and evolution. One significant discovery made by the telescope was the presence of fully formed galaxies much earlier than predicted by the standard cosmological model. This anomaly challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. Such findings disrupt our understanding, akin to encountering grandparents depicted as children in a story. Furthermore, recent evidence has revealed inconsistencies in major theories of the universe, such as the persistent errors in determining the Hubble constant. These discrepancies continue despite improvements in data accuracy and collection methods. New data from JWST has presented challenges to the current cosmological model. These issues highlight flaws within the model, raising questions among researchers and physicists. While the model has undergone adjustments in recent years to align with emerging data, some argue that these changes have been overly accommodating. Consequently, there is growing recognition that a paradigm shift may be necessary, potentially reshaping our understanding of the universe's fundamental properties. The Standard Model of Cosmology. The Standard Model of Cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe during the 1920s. Subsequent discoveries, such as the detection of the cosmic microwave background radiation in 1964, confirmed the Big Bang theory as the most plausible explanation for the universe's origins, portraying the early universe as a hot, dense soup of subatomic particles gradually cooling over time. Re-evaluating cosmology in light of new evidence. Achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. The concept of rapid expansion, introduced in 1981, was proposed to resolve inconsistencies in earlier Big Bang models, emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid, extraordinary growth shortly after the Big Bang. While specific issues are resolved by this theory, new challenges arise, particularly given the prevailing belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Certain phenomena, such as singularities within black holes, find indirect support. However, the remarkable discoveries of the JWST regarding galaxy formation and the ongoing problems with the Hubble constant raise concerns that we may be approaching a tipping point where a significant revision of our current cosmological model becomes necessary. This could require a complete reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. Cosmology, unlike many other scientific fields, grapples with fundamental questions about the universe, its origins, and our place within it. The study of consciousness and quantum physics similarly explores such topics, examining the intersection of theory and reality. It is crucial to question these foundational assumptions, given the impact of theoretical presumptions on data collection. History has shown that shifts in scientific thought, such as the transition from geocentrism to heliocentrism or the discoveries of evolution and relativity, have led to profound changes in societal perspectives. A similar shift in our understanding of the universe may be imminent due to an approaching scientific revolution in cosmology. Philosopher Robert Anton Wilson argues that theory becomes indispensable when further scientific inquiry fails to provide satisfactory answers. Ongoing research into cosmology may ultimately lead to the collapse of the current model, not due to empirical contradictions, but rather because of its inability to fully embrace new paradigms that reflect the latest findings. The current narrative must, therefore, be reconsidered in light of new evidence, as the JWST continues to reveal discoveries that may forever alter our understanding of the universe. JWST and the possibility of another universe. Neil deGrasse Tyson, a renowned astrophysicist and science communicator, made headlines with his comments on the JWST in relation to the discovery of evidence suggesting the possibility of another universe. The JWST, launched in December 2021, is a powerful space telescope designed to explore the universe in infrared wavelengths, allowing scientists to peer further into the universe's past than ever before. Tyson's remarks stem from the extraordinary discoveries the JWST is already making, particularly in areas such as the formation of the earliest galaxies, stars, and exoplanets. While Tyson did not directly claim that the JWST has discovered evidence of another universe, he referred to some of the intriguing and unexplained phenomena observed by the telescope, which could hint at something beyond our current understanding. One such phenomenon is the presence of strange, unexplained structures in the distant universe, which may suggest that the laws of physics as we know them could differ in other parts of the universe, or that the universe itself may be far more complex than previously imagined. This could imply the existence of multiple universes, as proposed by some theories in cosmology, such as the multiverse hypothesis. However, it is important to note that while these observations are fascinating, they do not yet provide concrete evidence of another universe. Rather, they open up possibilities for new theories and ideas that could redefine our understanding of space, time, and reality itself.